Okay, thank you everybody for coming. I know it's after lunch. Hopefully I'll keep you guys awake. I'm going to talk today about encrypted email and how hard it actually is. A lot of people, when we started doing email back in 2014, said, "Oh, you're doing email. It's been done, many, many times before, so it'll be very easy, right?" Turns out that's not the case. Since you guys are all technical, I'm here to share with you the technical difficulties behind encrypting email, why it's so hard, and how we have overcome some of these challenges in the past 4 years. So a bit of background about email. Really, why email is great and amazing. If you think about it, email may in fact be the most successful communication tool that's ever been devised in human history. I think it is the most widespread out of any communication tool that exists today. Essentially, everybody has an email account. Is there anybody in this room that doesn't have an email account? Right? Okay, so that's kind of what I thought. And because everybody has one, everybody also needs one. Email is also in many ways the original and most common form of identity. So when you go online today, your identity is not your passport number or your ID number, it's actually your email. And the great thing about email is it's completely free, it's an open standard, anybody can implement it, anybody can use it. So it's not a walled garden, it's not a closed system, it's open for the world. And that means there are almost no barriers to entry to email. This is actually a blessing and a curse, and I'll explain a bit more about this later on. The other thing about email that's very nice is that it's decentralized. There's no single point of failure in email. So there's no one service you can attack or hack or take down to bring email down. And it's also good because you have the whole ecosystem of tools that are already been built around email over the past 20 years. So this is why even though there's things like Slack, there's things like WhatsApp, and there's other services today, email is still very relevant. It's been relevant in the past 20 years. And we also expect that it'll be around for probably a lot longer than we expect. Yeah. Now, of course, we talked about how great email is. Now we need to discuss why email is awful. And it actually is awful in many, many ways. Let's go back to the design of email. SMTP was written down in 1982. So how many technologies do we use today that were still around in 1982? I think there's very, very few of them. And email is probably the only one that is still so widespread after 30-odd years. Yes. Yes, that's another one. Although I think the time is quite limited on that one. The other thing about email is when they were designing email in the 1980s, I don't think they really thought about things like security, online banking, hacks, because actually in 1982 the World Wide Web didn't even exist yet. So how email would be applied today versus how the designers thought about it is completely different, and this is a huge problem. Then there's the issue of RFCs. There's literally a dozen RFCs out there, and email RFCs are kind of treated as recommendations. And a lot of companies are not so good at this, but I would say one company that is very liberal in interpreting RFCs is Microsoft, right? They break a ton of rules, and they do it however they want, but they're not the only ones. So that's the second issue. Okay, so why do we care about end-to-end encryption? Why is it even relevant, and why are we even discussing this? Well, it really comes down to the value of your data. If you imagine the information that the email contains about you, all the places you've been, your friends, your contact, what things you've bought online, which flights you've taken, things like that. Email provides actually an entire and complete catalog of your whole life. And this is valuable, not just to governments, but also to corporations, and it's also very valuable to criminals. Of course, there's TLS, right, to encrypt email in transit. But actually, how many data breaches do we know occurred with data in transit? It's basically zero. Most data breaches targeting data at rest. So it's hacking a server and taking data off of server. And if you think about protecting servers and data breaches, it's not really a question of am I going to get breached or not? It's when am I going to get breached, right? It's inevitable. And this is really because if I want to protect a server, I have to guard every single entry point, every single door. If I want to attack a server, I just have to find one weakness to get in. So the odds do not favor the defenders. And this is why our assumption and your assumption and everybody's assumption should be that you're going to get breached sooner or later. And if you assume that you're going to get breached, the best way to protect your data is to not have it. And end-to-end encryption essentially gives you that. Then there's also the question of can't we have a lot of laws to protect our data? Well, the people you need to be worried about, like criminals, are generally the ones that are not following the laws. So your legal protection doesn't do much for you. And the last point, and very, very important, is that without privacy, you actually can't have democracy, because you need privacy to have freedom of speech, to be able to say freely what you think without fear of being monitored. And if you can't have that, our whole democratic society doesn't work anymore. So this is why we end-to-end encrypt, and this is why I think society as a whole needs to adopt more encryption. Okay, so now a bit about Protonmail, because I think that's what you guys want to hear, what we're doing, how we're encrypting, and why it's so damn hard. Well, today we're the world's largest encrypted email provider. That was actually quite easy to accomplish because we were the first ones, right? There's always a benefit of being first. But in fact, we're also the largest email provider now in Switzerland, which is our home base. We're a Swiss company. We're also an open source company, so everything we do is freely available to the public. We follow open standards. And the interesting thing is the company is completely financed by the users. And this is going to be quite important for reasons I will discuss later. This is a bit different from, say, Google, which is not funded by the users, but funded by the advertisers. So our overall mission is to create an internet that is more secure and also more free. And the overarching goal of what we do is this basic statement. We want to build an internet where privacy is no longer just an option, but also the default. And this is, I think, something that the world needs. I think GDPR, the European Union law that's coming into effect next week, will help get us there. But it's something that actually everybody needs to champion. And the only people that are going to do this are actually developers, like people in this audience, right? In the digital age, it's actually programmers who are the defenders of freedom and democracy. So this is a joint responsibility for all software developers out there to champion. Okay, so let's talk a bit about secure by design principles. If you read the GDPR, which I think everybody should do, but I don't recommend it because it's really dry and boring. This is one of the bullet points, right? Security and privacy by design. And when you're talking about building secure software, there's a couple things to keep in mind. The first point is that the user interface, the UX, matters. As scientists and cryptographers and engineers, that is not actually our first natural inclination when we think about security and cryptography, right? But the truth is, if no one uses your product, it's useless. It's not secure because it doesn't help anybody. So usability needs to be I would say, the first principle when it comes to thinking about secure software design. Second point is don't invent your own cryptography. It's for math people, it's actually very fun to think about the problem and try to innovate. But the reason you shouldn't do that is because cryptography is very, very difficult to get right. And it's very easy to make mistakes. So you want to use things that are been there forever, been tested forever, been attacked forever, and are known to be secure. So actually in cryptography, age is a very valuable virtue, because it means that it's lasted for a long time, which means it's probably secure because it survived attacks for longer. And then you want to also avoid what is called a security theater, which is don't build security things that have no practical impact, but you want to focus on security in layers. There's also going to be trade-offs, because if I always think about there's an axis where one side is usability and the other side is security, right? You cannot simultaneously have very good security and very good usability. There are going to be trade-offs. And a very, very important part of what we do is making sure that we have the right trade-offs. Then the other key thing that you have to do is you must educate the user on the threat model. And this is very important because if you want to know whether you're safe or not, it actually really depends on what threats you want to protect against. And sometimes you see advertisements, we guarantee your security. It's 100% hack-proof, right? You see things like this, right? It's military-grade encryption. Well, let's be honest here. Nothing is 100% security, right? By definition, that's not possible. So someone is selling you something that is 100% secure, run quickly, because it's not true. And in defining the threat model, you should also consider yourself as a developer or the service provider to be a threat. That doesn't mean that I'm malicious and I want to hack your emails. What that is actually saying is that I cannot guarantee that I will not be hacked. So I should assume that I will be hacked and I could act maliciously. So I need to not only protect data from outside hackers, I need to protect data from myself. So let's go a bit deeper into how Protonmail works from a technical level. There's really two parts of the equation here. There's the client side and the server side. So on a technical level, what we do is we generate all the encryption keys on the client side. And this ensures that our server, in fact, never has a copy of your private key. This means that all encryption, decryption, and signature verification happens on the front end. This is for all messages and all attachments. And everything before it gets uploaded to the server is encrypted on the front end. What the server does is simply access control. So it lets you know whether or not this person is allowed to access this data. But the data that's stored on the server is encrypted blobs. It's basically a ciphertext. And the server, what it does is it delivers the messages by moving around blobs of encrypted data. And also provides a public key infrastructure that allows you to query the public key of the person that you want to contact. So this is how we separate out the data to ensure the data is not accessible by the server. And under the hood, we implement the OpenPGP standard, because that's been around for a long time. It's trusted, it's secure, it's open source. So OpenPGP, there's an RFC for this. Luckily, just one. It's a major improvement from SMTP. And OpenPGP uses a combination of public-private key encryption and also symmetric encryption, right? So RSA is very, very slow. So what PGP does is it actually encrypts the large data with AES and then encrypts that AES key with RSA. And that's a way to get pretty good performance even with using public and private key cryptography. And we use what we called a layered access control system to control access to the data. So this is kind of the onion approach, right? In the outer layer, there's the public keys. These we don't hide. Anybody can access them. Anybody can query them. Then there's metadata and encrypted ciphertext. And this is, of course, on the server, which is controlled by the server and protected by the server. But again, most of that data is encrypted. And then the clear text, the things that you can actually read, is only accessible to the client side. So that's the most sensitive data that is only visible by you on your computer. And we do this, of course, with individuals, but it's also possible to extend this protection to organizations. This was new last year. It's been around for a while now. We're still constantly improving it. But since a year ago, we've made Protonmail available for companies. And this is actually quite interesting because it can allow you to protect all the internal communications within a company, within a business. And it's nice because there's two sorts of users. There's private and there's public users. So in fact, you can have end-to-end encryption, but still design it in a way that the admin, so the owner of the company, can in fact read the emails of the employees, but we can't read the emails and no one else can. And this is something that we see is becoming actually quite popular with GDPR because it's a way to make sure that your email is secure in the post-GDPR environment. Okay, now we have to talk about spam, phishing, and abuse. And when it comes to encryption, this is a really big challenge. Because if all your data is encrypted, how do you actually block and detect spam and phishing? This is one of the first challenges that we ran into when building Protonmail. And the reality is, if you build anything, people want to abuse it, and they will abuse it, and you need to find a way to defend yourself. And the reason spam and phishing is very important is, if we cannot block spam coming into our system or coming out of our system, A, customers are going to be very annoyed, and B, other email providers will not want to accept email from Protonmail because they'll say, okay, this is just a spam email provider. So we need to solve this problem. It's a very tough problem to solve, and our solution is again multi-layered, right? So we have problems looking into the very details of the messages because they're encrypted. But what we do instead is behavior analysis. So for example, you can see if an account is sending a lot of messages in a short period of time. You can check, for example, if the account creation country is the same as when it begins being used, because if that changes, that implies the account was sold to somebody else. And of course, you want to also try to stop the problem at the very front layer, which is prevent spammers from getting accounts in the first place. And you do that by using verification methods. So either CAPTCHA or email or SMS verification to ensure the people who are getting accounts are humans. And it's really this sort of behavior analysis, using actually some pretty sophisticated tools, that we're able to get a handle on spam. And through this alone, we've actually been able to get this problem under control. It's a constant battle, but it's way harder to do this without being able to read emails. And this is why this is a major challenge, not just for email, but any end-to-end encrypted system that we build. The other issue is a full text search. If my server can't read any of your emails, how can I actually do search on your messages? Because search is not something that you can do very easily on the front end in your device. If you have 20 gigabytes of email, you're not going to put all that on your iPhone and be able to check it there, right? So search is a massive problem in encrypted space, and users nowadays expect to have search. So there's a couple ways that we have approached this problem, and this is not a fully solved problem yet. So what we do now is you want to build a lot of tools for organization. So very, very efficient filters, very easy to use filters, labels and folders, so that email can be very easily organized by the user. That makes searching easier. Of course, we can search metadata, which helps us a lot. But the full text search of the message bodies, this is very, very difficult to do. And the solution that we have is, for example, on desktop, you're able to actually store all the emails locally, because email clients like Thunderbird and things like Outlook do that. So this is not a problem on desktop. The way that we're going to approach this on web and also in mobile clients is, instead of putting all the data and downloading it locally, we're only going to download the index. So you can index messages on the front end, and the index is actually much smaller than the full data set. And by encrypting the index and only using the index on the front end, you can actually do search over much bigger data sets in a pretty efficient way. And we're helped in this approach because every year phones get faster, bandwidth also decreases in cost. So a couple years ago, to download a 100 megabyte index would have been very, very expensive, very, very costly in terms of storage and bandwidth. But today, and probably in a few years, downloading 100 megabytes index on a mobile phone is going to be very, very minimal. And if we do a lot of optimizations, you can actually make the ratio between the index size and the full data set size quite good. So this is how we approach the search problem. But again, if you want to think about end-to-end encryption on anything you do, search is going to be a problem. And it's something that you have to think about before you start any project. Then there's a question of metadata, right? It's not really possible for us as a provider to fully encrypt all the metadata. And the problem is very simply described. If you want me to deliver a message to somebody, I kind of have to know who to deliver it to. So as a result, I know who you send the message to. And that's not a problem you can really work around. There's some very clever, difficult things you can do, but generally speaking, you can't solve this very easily. So this is why we cannot really do end-to-end encryption on metadata, and this exposes your metadata. And the way that we solve this problem is really by, again, a layered security approach. So first, we put the servers in Switzerland with some of the strongest data privacy laws in the world. We fully encrypt all the disks, so even on the hardware level, so that if someone breaks into the data center and steals the disk, then they still don't get anything. And then we put the data storage facilities in very, very highly secured locations. In this case, former Swiss military bunkers. This is, of course, this is basically the best you can do, right? Because you can't really encrypt this data. So the alternative is to protect it as much as you can. But this is, in fact, a limitation of email, because the metadata problem really cannot be solved in email, not at least in any very efficient way. The next thing is storage. If you're like me, you probably don't delete emails anymore. You maybe move them to archive, or you just leave them in your inbox. And this leads to what I call a rapid growth of user data. In fact, new users contribute data, and old users also accumulate more data. So the data growth curve has a very, very steep slope. In fact, it's not linear. In fact, it's actually a bit of a quadratic increase. And when you do encrypted data, you get some tough problems you normally don't have. One is compression works by looking for patterns and similarities in text, and then that allows you to compress data. But ciphertext, by definition, is completely random. So you can't really encrypt ciphertext. And this is actually a very big problem, because if you encrypt two identical messages, they also don't look the same if they're not encrypted with the same key pair, right? So in most email companies, the actual user data curve versus what they actually need to store on disk has quite very different slopes. For us, the slope of the user data and our on-disk storage is very, very similar. And this means that storage becomes much more costly when you talk about encrypted data. And this, for us, is actually a major cost center. Okay, and then there's what I call R&R. It's not for rest and relaxation. It's a redundancy and reliability, which is actually the opposite of rest and relaxation. If you're an email provider, in our case, actually, we have over 5 million users today. Uptime is very important. There's users in 150 countries, so there's really no non-peak hours when people don't need their email, right? They need the email all the time. And that forces you to have an infrastructure that is up 100%. Not 99.95, not 99.99, but literally 100. If you're down for even a couple minutes, you get complaints. And this is, of course, a massively difficult engineering challenge. This means that you must perform all maintenance online. And if you're an engineer, you know that really sucks, right? You can't take your systems down for maintenance. You cannot turn the network off. You cannot, shut all the servers off at one time. If you patch anything, it must be done sequentially. Everything must have failover. It makes your life very, very difficult. And that is just part of the business, right? Also, because for security reasons, we want to protect your data, we can't say, go to AWS, spin up 100 machines, and do things there. Everything must be done in self-hosted infrastructure. So that means when you need new servers because storage ran out, it's actually people putting the servers in, plugging in the hard disk, doing all the maintenance. So that makes your scalability also much more difficult if you want to do encrypted storage in the correct way. So our solution to this is, of course, a lot of time and money, but also, just the common industry standard ways of approaching this problem. So data centers, they must be redundant, right? A lot of people think, okay, data centers, they're so redundant already, they can never actually go down. Well, data centers, in fact, can go down. It doesn't happen very often, but again, for us, it can't even happen once, right? So you must be redundant in multiple sites. This is a kind of a key thing that is just a requirement. And then, because you can't have downtime, you don't have time to do what we call restore from backup. So the backups have to be kind of almost real time and replicated in real time. And that makes the backup strategy a lot more difficult. And this is why we always have at least 3 live copies of your data at any given time. So you can lose 2 live copies and still fetch it from a third location. And then, of course, you need automatic failover, automatic downtime detection, and automatic load balancing stuff. And the thing about these automatic failover tools is you need to test them regularly. It's not enough to build it and then test it once. You have to test it probably almost on a monthly basis to make sure that it's still working as expected. Because in a growing company, the parameters change, right? Your load this month is different from last month. So a failover that used to take 3 or 4 milliseconds maybe will take 10 or 20 milliseconds now. And you need to be able to detect that and change your strategy to account for that. So you need regular testing all the time. And that, of course, is also very difficult and very expensive. OK. Also, we talked a bit about UI in the beginning. UI is actually hugely important. And specifically in the business environment. A lot of business users, they have been using Outlook for decades. I once went to an IT department and asked them, what would it take for you guys to switch from Outlook? And the answer was, someone would have to die, right? And I think this is kind of true for a lot of IT departments. So you can't really go in and say, hey, replace your Outlook with Protonmail. Right? You actually have to find a way for them to get encrypted email, but still keep their Outlook. And that is actually a very tough problem, and that caused us to develop what we call the Protonmail bridge, because it turns out the best UI is actually no UI. And what I mean by that is if you find a way for them to do encryption without changing the Outlook or the user behavior, that makes adoption a lot easier. So the way that the bridge works is typically Outlook connects remotely via SMTP to a mail server. What the bridge does, it's a daemon that runs locally on each PC. So instead of connecting to a remote server to do IMAP, the Outlook client connects to a local IMAP server. And that local IMAP server is doing all the encryption decryption. So encryption decryption still happens on the client side, but via the bridge, you can still use Outlook without changing your whole user interface and user behavior. And this is something that we rolled out last year quite successfully. And it's actually nice because we have some government users now who are using Protonmail with a bridge, and their end users didn't even notice that they got switched to encrypted email. And that's kind of the goal that you want to reach. Okay, another thing of a technical curiosity, which is the tale of 2 passwords. No, actually 1 password. But a question that you might ask is, let's say I log into the web version of Protonmail, and then I log into the mobile app. How can my private key in the web version go to my mobile app automatically without the server being able to see it, right? That sounds impossible. And this is why we needed to find an innovative solution to do that, because I cannot tell a user, okay, if you want to use Protonmail on your mobile phone, you need to email the private key to yourself and upload it into your mobile app. That's very difficult. No one's going to do that. So what we actually do is we encrypt your private key on the front end. It gets sent to the server, which then sends it to the mobile device, and then you type in your password, and then you can decrypt your private key on your mobile device. So in that way, we can pass the private key through the server, well, the server having access to that key. Now, if you do this improperly, it's very, very insecure. So it's important to actually do this operation in the correct way. And the way that we used to do it was having 2 passwords, right? One password to log in, and then a second password to decrypt your key. And this was very easy to understand, very easy to implement, and it also ensured that the second password never got sent to the server. The issue is nowadays 2FA, two-factor authentication, is mandatory. So if you were using this system, you had to type in your login password, type in your mailbox password, enter your 2FA code just to get to your email. And again, user interface, right? That was too difficult for people to use. So we had to innovate here a little bit. And you might think naively, okay, why not just use the login password, also for the mail decryption password? Well, you can't actually do that either, because in the server, we'll have some information about what the mailbox password might be. So and also it's also kind of dangerous to do that because in fact, the mailbox password to decrypt your information, that's something that you have to use all the time. And that rests on the client side. So you don't want to call, make a call every single time and recycle the same session over and over again, right? So the solution to this is really you go from the login password and you use a hash of the login password to be the decryption, to protect the decryption key. And it's important here to use what we call a slow hash function. Because if, let's say, our database ever got leaked and we didn't properly use a proper hash here, then you would just take the database dump, run a rainbow table on it, and then after that, you can very easily break all the mailbox passwords. So it's important to use a slow hash function, and we use a form of bcrypt for our setup. And this is to ensure that people cannot take the data, put it in a GPU, and crack it very easily. So this is how we've worked around this particular issue. And actually, we use SRP also, secure remote password, as a way to further enhance the security here. Okay, so in the end of the day, like I said earlier, security is an onion. It's all about having multiple layers because there's really no one solution you can use to protect everything. So some examples of that. We frequently come under a DDoS attack. I don't know why. Some people think it's funny to attack Protonmail, but we see DDoS probably on a monthly basis. And in fact, the DDoS that we get are so big, the carriers in Switzerland can't handle them. So what we do is we use BGP to reroute the traffic, and we send all the traffic actually to Frankfurt in Germany, because Frankfurt has very big pipes. It's a main European internet connection point. We clean the traffic in Frankfurt before routing it down to Switzerland via private networks. And this is good to do BGP routing because this way, all the carriers who are doing the DDoS protection, only see encrypted traffic, and that's a good security measure. Another thing is, brute force attacks, right? Spammers, if they can find out, for example, the list of all PortML accounts would be great because they could send spam to PortML users, right? So they often brute force our API to try to enumerate all the accounts. So for this, you want to have randomized cooldown periods and rate limits. And it's important to be pretty random here because you don't want them to know that whether they're succeeding or failing. Because if you tell a spammer or attacker that their thing is not working, then they'll think of a way to work around it, right? So for example, you can do things like returning to them fake accounts that don't actually exist. So they think what they're doing is working, but it actually isn't working. And that's a very, very important trick, right, to keep them from trying to innovate or be more clever. Because the more dumb things they do, the easier it is for you to defend. Then, of course, there's also timing attacks, right, that can happen, and you have to again anticipate that your database is going to be dumped. So when you do things like that, you want to make sure that the data that you actually do store, so either sessions or tokens, things like that, are also protected. Okay, so on the topic of onions. we were one of the first email providers to actually make an actual onion site. And this is a way for you to connect directly to Protonmail through Tor. And the reason we did this originally actually was because we were under DDoS so often. So this was a way to reach Protonmail even when it was under massive DDoS. Because to DDoS us via Onion, you'd have to DDoS the whole Tor network, which is a lot harder than DDoSing just us, right? Of course, over time, we've gotten so good at DDoS protection that we don't get knocked down anymore by DDoS. But we still keep the Onion site because it's pretty cool. And if you're thinking about setting up an Onion site, there's a couple of things to actually keep in mind. One, people say, in the Onion site, I don't need TLS. I don't need SSL. Actually, you do, and you should use TLS for Onion sites. This is why we have HTTPS for our Onion site. And in fact, it is possible to get certificates for Onion sites that browsers will accept. So we did that. The other thing is you need to have a reasonable domain to prevent phishing. Most Onion addresses are completely random strings of numbers and letters. So if you show me 2 random strings of numbers and letters, and you change 1 letter, I'm not going to notice the difference. And that's a huge problem, right? Because phishing is one of the biggest attack vectors. So when we did our Onion site, we actually use basically our whole server farm, so maybe 1,000 CPU cores, to try to brute force so we were brute forcing the hashes to find a name that was very good. So we end up with a Proton iRocker XOW, right? That's a lot harder to phish because it's something that you can if I change a letter there, it's more easy to detect than if it was a random string. And actually, Onion sites are not hard to set up for a medium traffic site. But as you get to higher traffic, you run into another problem, which is how do you load balance a Tor site? You can do it, but it's a challenge. So that's something to think about, right? You don't want to do this on a very, very high traffic site. OK. So let's talk about trust issues, because a large part of Protonmail and anything in general is threat model and also educating the user about the threat model. So Webmail. Why is Webmail insecure? Well, the first thing is a malicious server, right? So it's true that your passwords never come to us. We don't ever get your decryption key. But what if I served you a fake web application or a tampered web application, which was secretly sending your password to my server, right? There's really no way for you to easily prevent against that. So you kind of have to trust us, and the goal is for you not to trust us, right? Or even worse, we know TLS is very often compromised. So what if someone broke TLS, had a fake certificate, and did a man-in-the-middle attack on your connection between your computer and our server, and served you a fake JavaScript that stole your credentials? These are risks that appear in Webmail, and this is why some people say using web crypto is actually dangerous, and I do agree to a certain extent. But actually, that's not a reason not to offer Webmail, because people expect Webmail. So if you don't offer Webmail, it doesn't work, because some people only use Webmail. So the way you solve this problem is you provide Webmail, but then you also provide more secure options for people that have a higher level of threats, people that have need a stronger threat model. So what we do is we also provide native applications, and also, for example, the bridge, which you can locally install, which avoids this issue, because the problem with the web application is every single time you visit the page, you load new code, right? But with something that's installed on your device, I cannot, for example, force you to change the code on your device. And that's how you have to address this issue. But this is an issue that exists with web encryption, and it's important to keep that in mind. The second issue is the trust of keys. I mentioned earlier that Protonmail serves as a PKI, the public key interface, right? So let's say I wanted to hack your account, or I wanted to read your emails. and you're emailing somebody else. In fact, I don't even have to compromise the JavaScript and send you, a fake JavaScript. All I can do is simply send you a different public key for the person that you're emailing, right? And it's a public key in which I control the private key. And then you're very, very easily compromised that way. And you wouldn't really know it because you're counting on us serving you the correct key. And this is a very, very hard problem to solve. It's an age-old problem. And this is why in the early days, there were PGP signing parties, right, to sign keys. The way that we've taken two approaches to solve this problem. The first approach is what we call a trust on first use model. And that means the first time you email somebody, it's actually possible to store their public key in an encrypted keychain that is linked to that contact. And through that fashion, you can detect if we in the future serve you a different key for that contact. And then that throws a warning for you, and you say, oh, okay, something happened here. I better call my contact to see, if something happened. And if you do digital signatures correctly, you can do that in a way that the server cannot cheat and lie to you. But that's actually kind of a hack, kind of like a half-baked solution, because it still requires you to trust on first use and verify the key the first time you use it. So the systematic solution, the complete solution, is what we call a read-only public registry. And this is something where you can actually leverage blockchain for this. So the idea is if you can build an online directory of all the public keys with a append-only a log that is immutable, then it is possible for me to secretly change your key. But you can see that in the public log of mutations. And this means that it's not possible for any email provider to cheat because they will be caught. And a very strong deterrent for cheating is to ensure that they will always be caught. And this is why solutions like Iconics that's being done at Princeton, or also Google's key transparency initiative, are steps in this direction. And that's also something that we're doing right now as a university research project. And if we can get that to work, that'd be very, very cool, because you don't have to trust in first use anymore. You can be sure that the key is correct because it's in the public registry that can be verified, and no single party can change without being caught. Okay, it's also very important, now that we talked about encryption, to discuss when not to encrypt, right? It's very tempting, especially as a developer, to say, let's just encrypt everything. But again, you have to think about it. If you encrypt everything, it's not accessible to you anymore as a developer. And encrypting too much actually takes away a lot of features from you. So for example, we could actually do some encryption of metadata, right? But if I encrypt, say, all the sender addresses, then I no longer can filter on those. And if I can't let you filter on sender, then that's kind of a problem for a lot of people when they use email. So these are some of the trade-offs that you have to make between security and usability. And there are always trade-offs, and it's kind of no one can tell you otherwise. And the key thing to remember here is, at the end of the day, if your service cannot really compete on features, it's not going to be very usable. So this is a key consideration when building any secure service: is what do you encrypt and what do you not encrypt? And this is a very, very hard decision, but is one that we pay a lot of attention to. Okay, then it's also interesting to talk about the business model. And what we've done today is not anything that Google couldn't have done, or Yahoo couldn't have done. But it really comes down to a very, very key thing to remember. On the internet, if you don't pay for the product, it means that you're the product. And what I mean by this is when you use Google, you don't pay. But in fact, the way that you're paying for Google is not with money, but with your data and your private information. So Google is essentially selling your data for money and giving you the service in exchange for free. And this is a huge problem. And this is something, this is why change like this requires really changing the business model of the internet. So for us, our model is different. We don't sell your data. because we can't sell your data, because we don't really have your data. We don't read your emails. Instead, what we do is we ask you to give us some money for the service. And some people, around 5% of people, do give us some money, but the rest are using it for free. And it's the people that pay more or less subsidize the free accounts. And I think, in the end, if you want to have privacy, you're going to have to pay for it. I know that's not what you want to hear, because everybody likes things for free, but it's the truth. And that's the reality that we need to come to terms with. Okay, so some final thoughts to kind of sum up. The first thing that I mentioned is still the most important one. If no one uses your service is not relevant, doesn't help anybody, doesn't make the world more secure. So usability is number one. It's something that a lot of people miss, and it's one that I cannot stress enough. The second thing is refuse to make perfect the enemy of good. Right? There are definitely ways to make Protonmail security more perfect, but it would actually make it less usable. And this is why we chose to make certain trade-offs. And the last point is, a lot of people have been saying, okay, email is dead, use Signal, use some other application, forget about email for secure communications. And actually, people haven't, there's articles actually from 1995 that say, email is dead. And this was in reference to, AOL AIM, AOL Instant Messenger taking over from email, right? So people have predicted the demise of email for 2 decades now. And actually, no, I think email will be around for a long time. And this is why we can and we should make it more secure. And this is what we're doing. And hopefully you guys will also support us on this mission. And together we can actually bring back privacy again to the internet. So that is our goal. So thank you very much.
Yeah, thank you, Andy, for this really nice talk. So are there questions?
Thank you for the talk. My question concerns, you talked about the trade-off of privacy and usability. To let the customer choose how much should be encrypted, so that there's an option. Is it technically possible, and have you thought about it?
Yes. Okay. Everything is technically possible, right? As technology people, I think we all understand that. It always comes down to a trade-off between time, effort, money, expense, right? So yes, in the future, we do plan to have options to have even higher levels of security, which would sacrifice some usability. But that would, that's essentially forking the code and making it twice as complex. So for now, we haven't done that yet. But as we grow, as we get more resources and we expand, that's definitely something that we're considering. And it's something that I myself, really want.
Okay, thank you.
One of the main challenges, I think, is also to get everyone into the boat, because communication is as secure as the least insecure contributor to the network. So if someone just says, okay, I won't use Protonmail, and he's not able to encode his emails, I just have to talk openly to him. So you said that your business model is that the ones who want more features subsidize those who don't want to pay. Do you think, in a long-term perspective, if you really want to make a global internet more secure, that the state has to somehow interfere and somehow say, like, if I have a car, I have to have an insurance, that if I want to write an email, I have to encode it?
Mm-hmm. Well, there are actually already laws like that, but they're mostly targeting certain sensitive businesses, right? Our long-term vision is that I agree with you. I think email, must be subsidized in some way, and it must be essentially given away for free. So in fact, I don't like to charge people for email. I think that's, in many ways a bad practice. But I also need to keep the lights on and keep the servers running, right? So our long-term plan actually is to sell more to businesses and also add other services that people are more likely to pay for, like file storage, and use that to subsidize the email to be completely free. And that's what I think that's what we have to do long term.
Hello, so thank you for your talk, and I wanted to ask a question about interoperability. So I'm curious about the way you detect if a communications partner which is not running Protonmail can receive encrypted email. And if there's a way, if you're running a service, if you're running another email server, if you can essentially publicize that you are ready to receive encrypted email.
Yeah, so there are projects that are working on this right now. One of them is called AutoCrypt. There's several others, and we're definitely very active in that space. Right now, the way that we support encryption outside of Protonmail systems is through PGP, right? So you can always do the manual key exchange and get that working. But the idea is that because we're using PGP standard, because it's open standard, in the future, more and more people can implement similar systems, and then you can have an ecosystem, using encryption across all email servers. That's, of course, a very long-term vision. It takes time to get there, but the reason we stuck with PGP, despite all its various issues, is because it does give us a path to that future.
Hello.
Yeah. Hi. Am I? Yeah. Okay.
You mentioned availability. Much like security, there's no such thing as perfect availability. So can you go a bit into the technologies you use to get the really good failover times, like the millisecond scale you mentioned, which is really impressive?
Yeah. Well, I'm not sure if it's exactly milliseconds, but it's generally on the order of a couple of seconds. So on the load balancer level, we use HA proxy, right? But there's ways to tune HA proxy such that failed connections are not dropped, but get properly retried, right? And then it also comes down to your network design, right? Because before it hits the load balancer, it flows through the network. So you can build your network in such a way that you can optimize the convergence time and minimize the number of packets that are lost, when you have a failed switch or failed router. It's a very technical question, but you have to very deeply optimize everything from the network layer to a load balancer layer, and also even to the application server layer. So you have to optimize on every single level.
Yeah. Thank you.
Yeah, there's no security without good randomness. Hence the question: what kind of randomness sources are you using / recommending?
Yeah. So. If you try to use, for example, Protonmail with the Internet Explorer 10, it'll tell you no. And the reason is because a random number generator on Internet Explorer 10 is broken. It's not secure, right? Again, all the keys are generated on the client devices. So we use the native random number generators that exist, for example, on your iPhone, on your Android phone, or on your web browser, because we have to support what the clients support. So in that front, we're not really innovating because we're not the ones generating the keys most of the time.
Hey. I was excited to hear that you are working on a blockchain integration of the security features. So I have a short abstract of a white paper suggesting that maybe you want to have email encrypted and used as a payment channel at the same time. So you can, blockchain and PGP, technically there are a lot of common concepts, and that business value would be like maybe have email order and payment, or have paid services over email, or even have spam protection by making each email cost 0.01 cent. Mm-hmm. Do you have any ideas in that direction, or do you think it's completely against the concept of free email?
Yeah. Well, that's a good question. We thought about it a lot. Right now, we're limiting the use of blockchains, in fact, to just the public key, right? So you put public keys in a Merkle tree, and you can put the signed tree root in the blockchain, right? And that's very basic. Your idea is to really extend that to all email communication, right? So every single email communication is essentially a transaction on the blockchain. And the issue with that proposal right now is that current blockchains are not so scalable. So the number of emails that are sent every single day are much larger than the number of transactions that most blockchains today can actually support. So the technology isn't quite there yet. We may explore it in the future, but we think there's several more generations of blockchains before we get to that stage.
Speaking of searching for metadata or in general emails, searching emails on your server, have you thought of trusted execution like Intel SGX or AMD SEV so that you can search on unencrypted data but securely on your mail servers?
Yeah, so we have also looked into that. There's also certain technologies that are doing that. Like for example, there's actually a project at MIT who is trying to spearhead that. And the main issue is that technology is not so mature yet. It's still too cutting edge. And in our industry, where reliability is paramount, in fact, we don't even use a current gen technology. We use several generations before because we know that that's actually reliable. So that's we're following it. We're involved in that, but it's too cutting edge for us to actually deploy in a production environment.
Any more questions? No, then
you said that you provide a public key infrastructure, and it's publicly available. So when I provide my key to this infrastructure, normally I promote my email address with my key. So it would be a perfect address book for any spammer in the world. So yeah, I think it's really hard to address the whole spam your users will get when they promote their key in the infrastructure. And you said a little bit less about spam protection. Could you please clarify how do you handle that many spam? I think you probably will face.
Yeah, so the way you do this and the strategies that are proposed in the papers is you stuff your tree with a lot of fake entries, right? So if you, for example, have 100 million accounts, but your tree has 10 billion entries, then it's not really efficient for spammers to try to query that tree and find the real accounts. And of course, you can also rate limit and force them to use a lot of IPs, right? Somebody mentioned earlier, IPv4. The reason IPv4 is still around is because IPv4 is a finite resource. IPv6 is essentially infinite. So then you cannot do IP rate limiting as effectively in IPv6. So combination of rate limiting, stuffing the tree with fake entries, and other tricks like this is how you approach this problem. But I agree it's not foolproof, but there is no 100% solution to defend against this.
So let's thank Andy again.